케빈 모라스 어플라이드 머티어리얼즈의 부사장님을 오랜만에 모셨습니다. 안녕하십니까?
Thank you for having me here.
한 2년 만에 다시 뵙는 것 같은데요. 그동안 잘 지내셨는지요?
That's right. I'm looking forward to doing this again.
지난 2년 동안 굉장히 그 산업의 변화가 많이 생긴 것 같습니다. 이 산업을 이끌어가는 견인차가 뭐 PC나 뭐 핸드폰, 뭐 이런 컨슈머 소비자용 제품에서 지금은 뭐 그쪽 수요는 많이 줄어 있고 거의 AI 쪽으로 투자가 많이 일어나고 있고 뭐 언론에서도 그쪽에 대한 관심도가 굉장히 높은데 지금 미국에서도 그런 거는 뭐 정말 잘 체감하고 계실 것 같은데요.
There's been a huge change in the last 2 years since we met. I think when we met before, ChatGPT probably hadn't been announced yet. So we had the whole ChatGPT moment that generated tremendous interest in AI, and that has only accelerated in the last 2 years. And the driver went from consumer mobile devices to AI-based devices. This is the focus of most of the electronic industry today.
예전에 2016년도인가요? 그 알파고라는 바둑 두는 그 프로그램 AI라고 하죠. 그거 했을 때 뭐 한편은 놀라기도 했지만 그때 당시에도 얘기 나왔던 것이 저 이세돌이라는 친구는 밥 한 끼 먹고 저 정도 두는데 그 뒤에서 작동하는 뭐 인프라는 굉장히 많은 전력을 소비해서 아직까지 AI가 진정으로 우리가 실생활에 들어오려면 아직 멀었다라는 얘기들을 많이 했거든요. 근데 지금 챗 GPT 같은 경우도 그런 LLM 기반의 AI도 비슷한 어떤 고민을 갖고 있지 않은가 하는 생각을 제가 갖고 있거든요. 어떻게 생각하십니까?
So yes, so actually that 2016 moment was where AlphaGo beat the Korean Grandmaster was a seminal moment. It showed that these programs can be can exceed human ability. And of course, the large language models have shown that AI can do even broader cognitive things. But both of these consume tremendous amount of energy. However, there's also a tremendous amount of societal benefit. So maybe the AlphaGo program on its own is only so useful, but the large language models like ChatGPT are much more broadly useful. And they do consume a lot of energy. So this will be one of the greatest challenges, how to get the benefit of AI technology while managing the energy envelope required.
최근 들어서는 이제 일반 인공지능, 과거에는 뭐 굉장히 멀었다라고 얘기했지만 지금은 이제 좀 가시화되지 않겠느냐라는 얘기들도 지금 나오고 있거든요. 요렇게 간다고 하면 제가 볼 때는 전력 사용량이 굉장히 기하급수적으로 늘어날 것 같은데 우리가 이 상태로 계속 버틸 수 있는 상황입니까?
So is it sustainable? I think not. With the current explosive growth in energy consumption, it is not sustainable. But we are assuming that the industry will not react to this. So the industry is addressing this challenge, and the way we're addressing it is by creating new devices that will have energy efficient compute at the device level, and of course at the architecture and the software level, there are improvements being made even at the software architecture level to have a more efficient compute capability. So the industry is responding to it across the entire stack to improve energy efficiency of these AI training models.
어플라이드에서 보시기에는 향후 몇 년 뒤에 에너지가 한 어느 정도로 우리가 소비를 해야 되며 또 그것을 우리가 지속 가능하게 하려면 어느 정도까지 좀 줄여야 된다고 좀 보십니까?
So we think energy efficiency needs to improve about 10,000x in the next 15 years. So how do we get to 10,000x, and is that even feasible? That is feasible. We've been improving energy efficiency by about 2x every 3 years in the last for the last many years. So that the number is feasible. And the way Applied is doing this is, we believe, by hardware. We want to enable the industry to have more energy efficient compute. And this requires more advanced logic, advanced DRAM, high bandwidth memory, advanced packaging technologies, as well as certain ICAPS technologies that allow for efficient power delivery from high voltage to low voltage DC without the normal losses that occur in that transmission.
지금 그 어플라이드는 되게 탑 레벨의 반도체 관련된 장비를 솔루션을 하는 회사인데 지금 말씀하셨다시피 지금 로직 관점에서 DRAM 관점에서 또 뭐 패키징 관점에서 지금 말씀하신 대로 좀 구체적으로 어떤 식으로 좀 에너지를 좀 줄이는 노력들을 하고 있는지, 그리고 그거 노력들이 과연 실현 가능한 것인지 좀 궁금합니다.
So let me give you an example from logic. So logic, the biggest inflection right now is the transistor going from FinFET to gate-all-around.
네.
That's now getting adopted at 2 nanometer. So we make a lot of the equipment that's used, about 50% of the equipment that's used to process these gate-all-around devices. And this requires new materials to make the gate structure, to make the contact, and various other modules over here. We are taking a look at each of these modules and, for example, to make the gate structure, you need to be able to make a transistor gate within a 10 nanometer area with 5 different materials. So you need atomic level precision to deposit these materials at atomic level precision to make a good working device. For contact, as these contacts are getting smaller, as these devices are getting smaller, it turns out the performance is getting worse. So we need to find ways to reverse that trend. So we are developing new equipment, new ways to address some of the challenges with contact resistance, to lower contact resistance. In fact, we made a new machine that combines etch and epitaxy together. And this reduces contact resistance by about 50% compared to the standard process. So we're looking at it step by step and making improvements in various areas to either enable these devices or to address some of the challenges with these devices to make them work.
플랫폼 형태의 어떤 컨셉은 과거부터 있었던 겁니까? 최근에 이렇게 나온 겁니까?
We have been doing some integration for a while, but we see today that as these materials are getting smaller, as the degree of control required at the interfaces is increasing, the number of interfaces is going up. Interface is basically the connection between one material to the other material. If you get any air or any contamination, it changes the behavior. And when the material is very small, this can have a big impact. So as the dimensions are getting smaller, more materials are becoming thinner and thinner, and there are more interfaces that interact with each other. And we find more equipment is improved when processes can be integrated. So we've been integrating processes, and today about 30% of our machines that we sell have some integration altogether.
지금 소위 얘기하는 그 파운드리 회사들은 뭐 대만에 있는 회사는 지금 3나노 GAA로 올해부터 이제 한다고 하고 있고, 삼성은 이미 작년부터 고객은 없지만 이제 뭐 그들의 이름으로 MBC, MBC 뭐 이런 이름으로 지금 GAA를 양산하고 있는데, 지금 말씀하신 그 플랫폼은 이미 고객들 사이로 들어가 있습니까? 아니면 좀 제안을 하고 있는 겁니까?
So we have deep engagements with all the leading foundry manufacturers for gate-all-around. And all of them sample our latest equipment, and they may decide to use it or not use it. But I can't speak specifically, I can't confirm or deny specifically whether one partner is using our machinery or not.
제가 이제 왜 이게 궁금하냐면, 요런 거를 이제 선보이시기까지 한 몇 년 전부터 이렇게 개발을 하셨던 겁니까?
We've been thinking about IMS for many years. I don't remember the exact date, but it was somewhere about 5-7 years back. Is when we created a program, a group to go focus on IMS. But we've been selling integrated machines for longer than that. It's just that we find now that this is even more critical. At the 3 nanometer node, at the 2 nanometer node, and below, the dimensions are so small that integrated processing is becoming much more critical. And so we are integrating where it makes sense, more and more processes together to make it easier for the device makers and to have better performance and better yield for the device makers.
그렇다면 GAA 다음 것도 지금 준비를 하고 계시겠네요. 뭐 예를 들어 CPET이라든지.
So the next after gate-all-around will probably be there for at least 3 generations. And after the gate-all-around, the industry is looking at CFETs. So CFETs are a close relative of related to gate-all-around. In gate-all-around, you have a NFET and a PFET side by side. In a CFET, you simply take that and you put it one over the other. In gate-all-around, initially all the connections are coming from the top, but then in the second generation of gate-all-around, they will do a backside power. So you'll have a PFET and an NFET connected from the top and maybe from the bottom. When you go to the CFET, you put them one over the other and make one connection from the top, one connection from the bottom. So the industry will take the similar technologies that were developed for gate-all-around and for backset power, and we will apply them with CFET. We have a very good roadmap to get there.
메모리에 대해서 좀 여쭤보려고 하는데, 이제 위로 수직으로 이제 올라가는 구조, 3D DRAM, 혹은 그 전에 잠깐 거쳐가는 형식으로 셀의 어떤 설계 변경 이런 게 먼저 거치고 3D DRAM으로 갈 거다 이런 식의 얘기들이 있는데, 3D DRAM에 대해서는 회사에서는 또 어떻게 좀 보십니까?
Yeah, so today the most common widely produced DRAM is what's called 6F squared DRAM, and it has a DRAM cell area and a DRAM peripheral area adjacent side by side. The industry is going to move to what's called a vertical transistor DRAM next, and in this case, the transistor, which today is like a U shape, will become a vertical structure, and the connection will be made from the bottom and the top.
네.
Also, the peripheral area will be moved underneath the cell area, so there'll be a lot of space savings, a lot of area improvements as a result. So we are actively working with our partners to enable this vertical transistor design because it requires new process steps to kind of fabricate these 3D transistor. After that comes 3D DRAM. So for 3D DRAM, as it's not possible to keep shrinking, for example, in the vertical direction. So the industry is going to move to a lateral direction, similar to like 3D NAND. But 3D DRAM is much more complex. It requires many new materials. It requires high mobility materials like epitaxy. So today the industry does epitaxy for thin layers, maybe 3 to 6 layers for gate all around. In 3D DRAM, this will become 100 plus layers. When you go to 100 plus layers, you need entirely different kinds of machinery. So we need to develop new machines, new technologies, new etching processes, new selective removal processes to make 3D structure. This is very complex. And we are working to develop these technologies. And we're also working to make sure these technologies are cost effective for manufacturing. And we also want to make sure the device works for our partners. So all of this is happening together in parallel.
3D DRAM을 구현하기 위해서 어플라이드에서 보시기에는 한 가지 가장 어려운 걸 뽑는다면 어떤 걸 뽑을 수 있겠습니까?
Oof. 3D DRAM has many challenges. It's very challenging. So the first challenge is to make epitaxy high mobility silicon with a very thick layer. And when you're trying to grow crystalline silicon in so many layers, it needs to be defect free, very smooth, so on and so forth. So that's the first challenge. The second challenge is you need to be able to etch these deep silicon layers, and you need to also do lateral etching of the removal of these materials to kind of construct the hanging areas. You also need to deposit selectively material sideways. You need to be able to make contact connections sideways. It is very complex. So the challenge with this is that it is not okay to just make one step. You need to make the one step and check if it works with the other 2 steps and other 5 steps. So this is why we are working across the company to bring different technologies, etch, epitaxy, CVD deposition, ALD deposition, annealing treatments, etc., bringing them together. And we're also working with our device maker partners, with other partners to make sure that all of this works so you can make a functioning device.
그러면 언제 정도의 3D DRAM에 대한 것이 가시적으로 파일럿 생산 정도라도 될 수 있다고 보십니까? 저희가 생각하기로는 굉장히 시간이 많이 걸릴 것으로 2030년 이후 이렇게 보고 있는 것 같은데 어플라이드도 그 정도 보시는 겁니까?
I think after 2030 is probably about the right time frame for 3D DRAM. There'll be a couple generations of 4F squared vertical transistor before it goes to 3D DRAM. But the industry will need to move to 3D at some point in order to kind of keep increased density.
하이브리드 본딩, 다이렉트 본딩 이런 것을 패키징의 영역이라고 봐야 되는 건지 BOL의 확장판이라고 봐야 되는 건지 약간 좀 이 학계에서 의견이 좀 분분한데 어플라이드도 그쪽 영역에서 굉장히 앞서 있는 어떤 기술력, 솔루션을 이미 고객에게 제공하고 있지 않습니까?
Yeah, so packaging is definitely a back end of line process, but the hybrid bonding is more like a front end, like a fab type of back end of line process, because you're making connections with tens of thousands of connections at a time. You need fab level defects, very low defects, particles. You need planarity, which is perfect to kind of make all these connections come down together. It is a different kind of back end of line. So if you can think of bumping, micro bumping, hybrid bonding is much more sophisticated in comparison.
어플라이드가 지금 잘하고 있는 어떤 솔루션 분야에 대해서 좀 소개를 좀 해주십시오.
So hybrid bonding is also very complex. Hybrid bonding requires bonding of the dielectric and the adjacent copper connection at the same time.
네.
And all these connections need to be made, like maybe thousands of connections to be made at the same time. So the key challenge with hybrid bonding is, first, you need to have a dielectric material that will stick to each other. That when you bring it together will fuse and make a strong dielectric. So we need to kind of engineer the right material. The next thing you need to do is you need to planarize very flat so that all these connections can come together and touch just at the right time. If the connections are not touching, you will be missing connections and the yield will be bad. Then you are now working with very thin die, like 50 micron die. So you need to handle these small die. And you also need to worry about defectivity that can create particles that'll prevent the connection of these materials. So you need to have very clean front end fab like working environment, and it's necessary to then do treatments, plasma treatments, and annealing steps to kind of clean the surface and make it stick together and anneal. So all these are huge challenges to make hybrid bonding work. Luckily for Applied, we have most of these technologies in-house. We are leaders in dielectric CVD. We have very good treatment capabilities in our treatment product group. CMP, we're the leaders in CMP, chemical mechanical planarization. We didn't have a bonder in-house, but we've partnered with Bessie to kind of incorporate their bonder on our tool as well. And so we are now putting all these technologies together.
그런 솔루션 한 곳은 제가 볼 때는 지금 뭐 배시랑 이렇게 협업을 하신다고 하셨는데 지금 어플라이드가 거의 유일하지 않습니까?
Yes, we're collaborating with Bessie and putting all these processes together. Applied Materials saw the need for this before anybody else did. That's one thing about Applied. We tend to kind of see these challenges early. We tend to start early. But then it is also true that after we start the process, other people see the approach we're taking and then follow the same approach. So today I will say we are the leaders in this integrated bonder technology. You can do some bonding without integration, but it's not as effective as when it's integrated. And so we're integrating this together, and we are the leaders in the integrated bonder right now.
지금 그 말씀하신 그 하이브리드 본딩, 다이렉트 본딩 같은 기술이 지금 로직에도 이미 지금 일부 소량 어떤 제품들은 적용이 되고 있는데 앞으로 어떤 영역으로 좀 확장해 나갈 거라고 보십니까? 지금 뭐 예를 들어 HBM이라든지 또 뭐 낸드 플래시라든지 이런 쪽으로 지금 확장이 계속 되고 있는데 어플라이드는 어떻게 보십니까?
So maybe let me clarify kind of where hybrid bonding is being used today. So there is some adoption of hybrid bonding in logic for some small number of chips or chiplets together, but it's limited in its amount of usage. In DRAM, all the HBM today is still being manufactured with microbumps, so it is not using hybrid bonding yet. But NAND is starting to, and certainly there's one NAND customer that uses wafer-to-wafer hybrid bonding. The biggest challenge, though, is when you're dealing with like logic or DRAM, when you're trying to do die-to-die hybrid bonding.
No.
That's a much bigger challenge. And so that's where our focus is. We think that the integrated hybrid bonding solution that we are developing is a right approach to give you high yield in these very expensive, DRAM is expensive, logic chip is very expensive. You want to make sure the hybrid bonder gives you very good yield at the bonding. So that's the area we're focused on.
제가 이건 개인적으로 좀 궁금한 건데 다 어렵겠지만 웨이퍼 투 웨이퍼가 어렵습니까? 웨이퍼 투 다이가 어렵습니까? 다이 투 다이가 어렵습니까?
Die to die is the most difficult. So in die to die, each die needs to be cut. And of course, when you cut the silicon wafer, you can have defects that can create particles that can get in the way of the connection. So die to die is much more complicated than the wafer to wafer. Also, the alignment will be a little bit more difficult when you're doing die to die compared to wafer to wafer.
지금 로직에 대해서, DRAM에 대해서 또 이런 앞으로 차세대로 불리는 하이브리드 본딩 뭐 이런 쪽에서 어플라이드의 어떤 혁신 사례 뭐 이런 적용 이런 뭐 내용들을 말씀해 주셨는데 이 모든 것이 다 이루어지면 아까 말씀하신 AI로 인한 전력에 대한 폭증 이거 해결할 수 있습니까?
Yes, so actually, all of these innovations we're talking about will improve energy efficiency. So gate-all-around improves efficiency by double digits. Same for HBM. By creating HBM, you have higher bandwidth for these AI devices. The innovations we are creating allow for the creation of gate-all-around as well as backside power devices. Both of these type of innovations in logic will improve the energy efficiency by double digits in each case. With the vertical transistor and 3D DRAM as well as with HBM, again, these innovations are going to create higher density, and through HBM you can get much higher bandwidth closer to the logic CPU or GPU chip. And of course, advanced packaging. Advanced packaging allows all these devices to come together much closer together. It reduces the energy losses in communicating off-chip when you bring chips closer together. So we are very confident that our innovations will have a direct impact in improving energy efficiency for these devices.
지금 현 세대에서 양산되고 있는 기술은 한 10년 전, 15년 전, 20년 전에는 사실은 구현 가능할까라고 의구심이 들던 기술들이 지금은 어쨌든 엔지니어들이 열심히 노력해서 양산화가 되고 또 우리 실생활에 뭐 이런 제품이나 다 들어가서 이제 저희가 쓰고 있는데 보통 이런 신기술 같은 것들이 한 어느 정도 주기로 개발이 되고 양산에 적용되고 하나요?
Well, that's a great question. So we are seeing that typically it takes 10 to 15 years from innovations in a lab to go all the way to production. And that is, I think, being optimistic. So when a university comes up with an idea to taking that all the way to a production device is about 10 to 15 years. That is a very long time.
Long time.
And as an industry, we need to find a way to make this shorter. So seeing this problem, we are trying to bring our industry together. We created this concept called an EPIC platform that allows us to bring our device partners, university researchers, R&D labs, material suppliers, and design houses together. So we can, in one area, co-innovate to address some of these challenges. The biggest problem today is when university does the innovation, then they pass it on to the equipment company. The equipment company will do development on machinery. They will pass it on to the device maker. The device maker will evaluate it, and so on and so forth. It takes too long with the sequential process. If we can experiment and overlap these processes together in one location, we can accelerate the development. So we know this works because Applied has been doing this in-house today with many of our technologies. We want to make it more democratic, more inclusive by bringing other partners together to accelerate these innovations.
에픽 플랫폼은 언제 설립이 지금 돼 있는 겁니까?
So it's something we announced in 2023, but the company is already operating this way. So in 2023, we announced Epic Silicon Valley, and we're actually building a facility, a new center to house, to expand our lab facilities and to allow for space where our partners can come and collaborate. However, we've already started to work this way. So as I mentioned earlier on the packaging example, we're working with Bessie. That's an industry partner. We've also worked with Screen. Screen is a Japanese wet clean company. to co-innovate with us. We worked with the university in that case to come up with some new ideas. And between screen and applied materials, and also some R&D labs like Albany Nano in New York, we worked together to try some new integration scheme, new equipment and new integration scheme to make a better result. So in many ways, we're already working there. Packaging is another example. Packaging, we have a lab in Singapore where we are working with IME, the Singapore Research Institute, and we are bringing, again, our partners together, materials partners, equipment partners together to co-innovate some of the new packaging solutions. For example, the advanced packaging tool is in Singapore. So although we are still building our new facility, our EPIC facility, we are already working in this mode with our industry partners.
돈 많이 쓰시겠는데요, 그쪽에?
It costs a lot of money. But we think at the end of the day, it will save the industry money. Because if it takes 15 years to get a return on the investment, but you can get the return on the investment in 7 years, which is better?
한국 기업들 중에도 혹시 참여하고 있는 기업이 있습니까?
So there are many Korean companies engaged with us in the EPIC platform. There are many Japanese and American companies also engaged with us. So when we launched the EPIC, when we made the announcement in 2023, we had leaders from several Korean companies engage with us, participate with us as well. And this is also something where we want to encourage more companies to partner with us. So yes, we want to engage with as many companies as we can.
예, 오늘 케빈 모라스 부사장님 모시고 반도체 산업 혁신에 대해서 들어봤습니다. 다음에 또 기회 되면 한번 또 나와주시죠. 지난번 제가 또 나와달라고 부탁했더니 오늘 또 약속 지켜주신 것 같아서 감사합니다.
Well, thank you for having me back. And, I'm happy to come back and talk again next time I come down. It's always interesting to talk to DLEC and your viewers on YouTube.
감사합니다.
감사합니다.